subfield. So problem 28. So first we have a definition here. Okay. And definition is that of a prime subfield right. A subfield of F or fields containing yeah, fields sub F. Uh, Wait a minute. Oh no, you are right, na? Intersection of all subfield. Yeah, sorry. Yeah. I mean it has to be that because it's subfield. So intersection of all subfields of F. No, that's the yeah, correct. So okay, let us see. Show that this subfield is the quotient field of the prime subring of F. So show that this is the quotient field of the prime subring of F. And prime subring is the intersection of all subrings of R. Okay. Show that this intersection is a subring that is contained inside all subrings of R. Moreover, show that the prime subring of R is equal to n dot 1, where 1 is the multiplicative identity of R. Let F be a field characteristic P. Show that the prime subring of R is isomorphic to the field FP if characteristic of F is equal to 0 and the prime subring is isomorphic to Z otherwise. Okay, so these facts we will assume about prime subring. Is that fine? These are the facts that you expect. Okay, so yeah. So we will assume, just to repeat, for myself say, is that if I'm taking a field F, then the prime subring is just the smallest subring, and it is either going to be Z or it is going to be ZP. If it is characteristic, if F is characteristic P, then it will be ZP, otherwise it will be Z, which is what it should be. So this is fine. So of course, those are a separate set of problems to do maybe, but we will assume it and do this problem. Okay. Now show that this subfield is the quotient field of the prime subring of F, that it is contained. So I'm just the rest of the problem I'm saying that it is contained inside all subfields of F, because by definition, and that it is isomorphic to Fp or Q depending on whether the characteristic is P or 0. Okay, of F is Q. Let's just do this problem. So let's assume that characteristic of F is 0. Okay. Uh, yeah, you're right. It's a trivial question. That's what you mean, maybe. So the reason why I'm saying it's trivial because Q is obviously so Q is a subfield of F. That is true, right? And any subfield F1 of F implies characteristic F is 0. That implies Q is contained in F1. That implies Q is contained in the prime subfield. But that implies Q is equal to the prime subfield. Because Q is contained in every subfield. Yeah, maybe it's better to write here. Because this is like the definition because Q is contained in every subfield. F1 contained in F implies Q contained in F. That we know every subfield of every field of characteristic 0 contains Q. So then basically by definition, it's contained in every subfield, so it is the prime subfield. That is an equivalent definition, right? This definition is by intersection, but we can also take this definition. We can separately prove they are equivalent. Okay. Uh, yeah, that is true, but that I have already written here. Right. I mean, I'm saying that it contains Q. You are saying it contains Z. Right. So that is contained. Yeah, that and what you're saying, you can use it to prove that it is Z. The prime subring is Z. Uh, yeah, exactly. So here I assume the characteristic is 0. Just to simplify the question. Otherwise you have to look at Z mod P. Yeah, correct. So that is similar. Oh, I get it. So basically you are doing both the cases together, maybe. Yeah, but I'm just separating it. It's the same thing. Yeah. If you do like that, then also you get ZP. It's easier there because there is no Q. ZP is both is field itself. So yeah, right. So anyway, this problem is absolutely trivial, I would say. Yeah, so let's move on to problem. Actually, maybe some of the previous problems that involve some calculations we should do. So because these are general facts about characteristics and so on, so they will not be very difficult. Mm, yeah, actually, all these are easy only. I'm just looking at the questions. Yeah, let's do this one. So problem number 8. It's for finite extensions. So see, I'm just choosing the problems that look that look like that I think I should do. Okay, but you can look at the rest of the problems later. It's up to you. Okay. Yeah. So this is problem 8. So let k let k equals fa be a finite extension. Okay. Finite extension f. Now for alpha in k, let L alpha be the map from k to k, which is multiplication by alpha. So fix alpha in k. Let L alpha be a map from k to k defined as multiplication by alpha. Okay. Show that L alpha is an F linear transformation. Also show that determinant this characteristic polynomial is the minimal polynomial of A. Okay. Show this determinant minus L alpha. So here, of course, L alpha is being thought of as a matrix, maybe, or wait, what is LA? Oh, I'm sorry. Yeah, let's see. Mhm. So we are taking alpha equal to A is the minimal polynomial mean. The notation is F. So over F A of A. This is the notation for the minimal polynomial. So I'm just following the notation that they're using. There's one more part, but let's do this. Yeah. So let's do it. So this part that it is an F linear transformation is fine, right? So this is okay. It's F linear. It will, is it uh is it also k linear? Yes, right. It is also k linear, but that's not important maybe here. Yeah, it implies it's F linear, but anyways, so this part is done. Good. Let's do this. So as I said, that this LA is being thought of as a matrix now, and then you can talk about this determinant. You can directly talk about determinant of transformation. So is it clear? So obviously you have to use Cayley's theorem first, meaning that, like, what do you want to show? You have Px equal to this determinant, right? When you have two goals. You need to show that P of A is equal to 0, right? You want to show that this polynomial has A as a root. This is Cayley's theorem, right? Yeah. So this is true, means Cayley Hamilton, not the Cayley theorem we were doing yesterday. Cayley Hamilton. And now we want to show that it is the minimal polynomial. So how do you do that? That you can do by degree arguments, right? Otherwise, it's not so obvious that it is irreducible, right? Directly. Means if it's irreducible, you are done. If it's F irreducible, you are done. But I don't know how to show that. But as I said, you can do degree things. So degree of P is equal to, what is the degree? Is equal to dimension of xi minus La, meaning dimension of this matrix, okay? But that is same as the degree of the extension. Yes, right? So this is fine because as a linear transformation, so the degree is this degree because, yeah, over F we are doing. So that's it. So then you are done, right? So you have a polynomial which has this as a root and its degree is this. So it means that its degree is equal to the degree of the minimal polynomial. So it is the minimal polynomial because this, you know, is the degree of the minimal polynomial. Just expanding it, okay? Right? You know this, that I think I'm just oversaying, so okay. Here I mean, if you have not done this kind of problem earlier, you see that this is something nice, right? The uniqueness of the minimal polynomial, which has its roots in Euclidean division, is allowing you to show that something is irreducible or something is minimal, right? I find that very amazing, that because showing that something is irreducible, something is a prime, is maybe initially not so easy because you're not factorizing or anything, right? But you going the other way. You're kind of using another way, which is very different in some sense, right? That the degree of the extension is the sort of determines the degree, is the degree to the minimal polynomial, right? And that degree of extension you can manipulate with linear algebra, like you see here, or even earlier, there are degree formulas and so on, right? So this is a very nice thing, something which is about irreducibility, factorizability. You are somehow encoding it into linear algebra, and then you are able to use that too. Yeah. solve the problems. I find that very nice. Right? That's one of the things. Yeah. So I'll not do other questions, but maybe we should take the time and just look at few things that you can think about here. Because first of all is the determinant, right? This determinant of a linear transformation. Maybe this is one of the things to I just want to say. Meaning, how does determinant come? Obviously, there are exact formulas and matrix theoretic view, but let's think if you want to give a basis free description of determinant. Let's see, I do not know. I mean, I can collect everything I know. So how that's, I mean, you can tell me if there is some other way which you see the determinant. So obviously the determinant is a number, right? It's a number, and it's obviously there is the theory of alternating k multilinear forms, right? And from there you can get the determinant. So, but uh, is that basis free? I think so. And you can get the determinant up to a scalar, up to a scalar factor. So maybe I can say that, right? So yeah. So yes, and even then we can say it in terms of tensor products, right? So it should start with the finite dimensional vector space that V be yes. And this viewpoint, which I'm going to just say a little bit, is essential in differential geometry. Okay, so when you do multivariable calculus, you're doing, or when you do after that, the next thing is of course to do differential geometry, because uh, multivariable calculus is like everywhere a world is same. That's its assumption, right? Everywhere things are same. So, but that's not how it is in reality. And differential geometry is model some tries to model something like that. It's like the next easy thing after multivariable calculus, and there this is very essential. Okay, because otherwise you cannot do any integration. You can do differentiation maybe, but you cannot do integration without these alternating forms. So anyways, if let V be a finite dimensional vector space, okay, then I am going to denote the dual by dual of V by this. Okay, no, this is probably not what I wanted to do. So I'm going to just denote maybe by this. Okay, this is just going to be V dual as you know it. Okay, and the V dual is just the one linear maps. Okay, but then I am going to look at this. Okay, and this is going to be tensor product. So use the theory of tensor products that you know, and to see that this is the same thing as collection of, and this is actually still in in standard linear algebra bilinear forms, collection of all bilinear forms. I'm not proving this. This you can prove, but it is a deep. I mean, it's easy to prove here, but it's actually a deep fact. It's actually a deep fact. Yeah, yeah. You in overfeeds everything is true, but when you ask this later, it's actually a deep fact. So, anyways, you look at this, and just to say like how uh, I am interpreting this. I'm not showing that it's going to be an isomorphism, but I need to show you the interpretation to do the calculations. Like if you take f and g in this, then you look at this. And how do we define this? That's what I need to tell you. Do I mean, it is, yeah, exactly. I need to say how I'm interpreting this because this is not a function or anything. It's just an element in this abstract space. But how I'm interpreting it as a bilinear form, I need to say, which is of course the again the only choice you have. So if you're going to interpret it as a bilinear form, then obviously you need to do this. You agree this is a very natural definition, right? But it's the definition. Okay, this is the definition. This is the interpretation because because this thing, if you see, or rather, this interpretation that I've given you, right? Then this thing is living where it is. Uh, it is living in is actually living in this. See, yeah. But yeah, but that's what I wanted to show. So, anyways, this, so this way you build up. So you from the one linear one forms, you get two forms, and these are called forms or two bilinear forms, trilinear forms. And in this way, you can just go as high as possible, and you get as large as you want, and you get k forms. So this way you get k forms. How does the determinant come? Okay, so the point is these are all just forms, and they are not alternating necessarily, right? So we need to look at alternating forms, right? So that's the question. But just before that, you can check that this the dimension of this is, any guess, n to the k. Right? You can prove that inductively. It's n to the k. But now we need to look at alternating forms, and that was sort of necessary to say this in some way. And so I want to say about alternating forms and then say that the dimension of n alternating forms on an n space is one dimensional, and that one dimensional space is spanned by one vector, and that one vector is the determinant function. Okay, so it's just a rough view, and there are many references, but you can look at, because I think you're already reading multivariable calculus. So Spivak's book is there, and it will have this calculus on manifolds, which is the standard book on multivariable calculus. First few chapters are multivariable calculus, and later is also multivariable calculus, but it's just on it's on manifolds, I think. Not really manifolds, on n surfaces, which are simpler cases of manifolds. So calculus on manifolds. I think I may have suggested this book earlier at some point. But yeah, this material will be there. If you look at some multilinear algebra book, it will be there, certainly. Might be there in Hoffman and Kunz. Yeah. But I will just say about this alternating forms and you see. So why we are doing all this is to get an interpretation of the determinant, a basis-free interpretation of the determinant. And these are deep, like very important things. I mean, in mathematics, these are the things which you see. It's very very important also. Other than maybe very fascinating. So alternating forms. So obviously you know the definition, right? So maybe just an alternating two form and alternating two form is going to be what? It's a map from V cross V to F T such that this happens, right? Now the goal is to take yeah, so maybe I will just first say this, then it's better. You look at alt KV. This is the space of alternating K forms on V. Okay, so this is the just a notation. Okay. Now the interesting question is, how do you construct these spaces naturally from the space of bilinear form, so from the space of K linear forms? How do we do it? Okay, so they just what to do is you want to take a K linear form. You want to take a K linear form, which is, let's denote it. What should we denote it by? Any suggestions? Omega, T, suggest something. Omega. Let's say, let's not take T. Let's take omega. Okay. Yeah. Is it fine? Let's take omega. Okay. So what are we doing? What are we doing? You are taking a K form, which is a K multilinear map. So what is my omega? Let's see. So omega is nothing but a function. It's a function from V cross V cross V or V tensor V tensor V. So it's a function like this. Right? This will be a number. Okay. And omega has these beautiful properties that right. This is fine, right? So it's always easy, right? It's exactly it's K linear, so it's linear in every variable. So those are the things that omega has. But now you want to take it and you want to somehow return something which is alternating. Okay. This is important. You want to connect these two things, right? You have a separate theory of alternating forms, you can define, you can compute everything. But using using the k-linear forms, if you do, then all the computations about alternating k-linear forms come from the work already done on the k-linear forms. That's why we want the connection. So how do you connect them? So it's like this, which is, I mean, if you sit down, you can motivate it, but I'm just going to write it maybe. So it's going to be something like a character sum. So it's representation theory kind of notation, but it's doesn't need anything like that. Sn, and you do -1 to the power sine of the permutation, because you know you want to make it alternating, and alternating means that when you push the sign, when you have a v1 up to vn, and then if you do v sigma 1, v sigma 2, v sigma n, then that related to v1 up to vn, it should be related by the sign. That's what alternating means, right? So if you just reduce it to case of two variables, you can just see that's the definition. So this, and of course then you have this. This, right? And and we this is not necessary, but it is later, it makes some formulas very nice. Okay, this is a this you can prove. I mean, so do you understand what this is? So because I've not defined it properly, I should say that this goes to, so from omega I'm going to a different I'm going to a alternating form, and that is defined as, I'm using the notation alt omega, and alt omega at v1 up to vn is defined like this. Okay, maybe it's still not well said. I'll just try once more. So I'm just doing omega going to alt omega. Okay, and alt omega is defined like this. Is it fine? And this is not some difficult thing. If you do the two case, you see that this is how it should be. I think you can already kind of see that it's something like, you may not have proved it, but it looks good. It looks like it will be alternating. Change two variables and see, just changes the sign. And this one is fine. This one, one may not foresee it, but one doesn't need to. When you go later and when you want some nice formulas to hold, then you this putting this factor here is good. It's not necessary here for it to be alternating. I mean, that doesn't affect whether it's alternating or not, right? Because the space of alternating forms is a vector space, so any scalar multiple should not affect it. But still, we keep it there. Okay. So this now, what else should we do in this alternating game? We need to describe the dimension and so on, right? But just like we had some kind of a calculus here, this is obviously also, if you have done graded rings and so on, then you will see that you will you can there is something called a tensor algebra, which can be defined like this maybe, and these are its graded components. So when you do graded rings, you will this will be a prime example. Okay, so, I mean, prime simple example. There are other complicated examples, but this is a simple. And of course, a polynomial ring is a graded ring, and so on and so on. This is a very good. But what my point was not to say about graded rings. My point was to say this: that what are you doing here? You see, you are taking one form and you have a very nice way to get to two forms. Taking two forms, you have a nice way to get to three forms. So you're able to combine forms of lower dimension and get forms of higher dimensions. Agree? Right? And that's like a very beautiful picture. I mean, that tells you everything. It tells you the dimension. It tells you many things which, when you investigate and read, you can see that it's really there. We want to do something similar here. And that is where the new thing happens. So that's called the wedge product. Okay. And initially, I wanted to say about this using wedge products, the determinant directly in terms of wedge product, but somehow I'm not able to. Wedge product. So this is basically the multiplication for alternating forms. It's a way to take two alternating forms and give you another alternating form. Okay. So this is going to be a map alternating K forms on V to alternating whatever L forms on V, and I want alternating K plus L forms. And the previous things are going to be helpful here. Yeah, there is a yes, right. Now I see it, but I'm not going to say that today because I mean, the point is to say things in a sensible way. If I say that now, it will not be sensible. But soon you will see that this wedge product can be directly used to define the determinant. Okay. So because it's a very natural thing, and this wedge product, if I have to say a few words about the wedge product, it's a game changing thing. This wedge which you're going to see, this is really changes the picture a lot of things in mathematics. Okay. Yeah, it show up everywhere actually, even somewhat in physics also, which some things which I'm starting to read, and there this same principle shows. Okay, but so you may have heard of supersymmetry from string theory, right? So that they used to define something called super manifolds, and their tangent space they called supergroups. And now people want to understand some category theory of supergroups. And so let's see, because I do category theory, but not of supergroups. Of course, I don't know, but now that's a new thing to study apparently, to do research. But let's see what's to come. But yeah, there are a lot of things. But so here, what we want to do is we want to take to. I'm just using a notation which I know from before. So, and of course, this is critical in also differential forms, which is built on these forms, these static forms, sort of. They're like static forms. So when you, this is the notation only. This is, you have to define what this is. Still, I've not told you what this is, but you can guess it, right? If you want to take two forms and you want to define this, how should this be defined? Okay. So it is like the tensor product, but you have to just alternatify it. Okay, so I'm sorry. So this is, let's see, this, and what you do, I hope is correct. So you, yeah, so what you do, you do omega tensor eta, okay, and you apply the alt. And I will just expand this because this may not be completely obvious. And you have to also add a factor which actually I don't remember. But what does this mean? This first means that you have to, so you understand this. This I should say. So this is basically like omega will take the first k things. Okay, naturally, and eta will take the last healthy, right? This is how it should be. But then you have to alternatify it to get an alternating form. Yeah, what else? Otherwise, you will not get an alternating form. It will not be alternating. Right? And that's why you use the previous definition to alternatify it. Okay. So yeah, so this is the story, and I will suspect that you will have to, like, naturally you can guess, right? You have to attach this factor because balance things. Yeah, you understand. So this is going to be the definition of wedge. And now you should read and see that this has many interesting properties. And some of the property would be that, or the consequence would be that the dimension of this space, and this is amazing. I mean, even like to prove identities in combinatorics, when you prove like in representation theory, you use the fact that they are coming from in this kind of space. And choose K. And this obviously implies that there is only one. And so this space is finite. I mean, this stops. After some time, the dimension is zero. So you don't have n plus one alternating. So you don't have a n plus one alternating form on n dimensional space. It is not surprising, right? Because if you have, then two vectors will be linearly dependent, and then the will become zero. Because right? I mean, the determinant, right? If two rows are same, then the determinant is zero. This is like a larger setting in which it is true, and from there those things follow. One is, I'm not saying you need one to know the other, but it's just a connection that it's part of something larger. Okay. So, anyways, it's just what it is, and this is this. And so that this means that there is only one alternating form of one n alternating form on n dimensional space. One meaning that other the scalar multiples of it. So this implies that, to say it properly, all that I'm not proving that the work to do, but this is basically there is one form, one function, and you can call it omega, okay, and others are lambda, means some real multiple of it, okay, fine. And so this is the thing, and then you choose that omega. So now you have to fix a basis. You fix the basis, and maybe you take the standard basis 1 0 0 0 0. So you take that omega such that which returns 1, and this omega is defined to be the determinant, right? There will be such an omega because you can scale it and find such an omega. Take any omega and scale it so that this omega becomes like this, and that omega is a determinant. Okay? So you need a basis. I mean, to define the computationally get the determinant, you need the basis. You need a basis. You cannot do it without it. But to get the determinant up to a scalar, a 2 times determinant, 3 times determinant, you don't know that times. Okay, that follows from the theory. Okay, and that scalar is not really important for mathematicians. Yeah. Okay, so I'll stop here, but you can look at this and think about these matters. There are many interesting directions one can go, but okay, so I'll stop here, right? And if you have any questions, then you should ask now or you can ask later. Yeah, I did not go into the other thing which I wanted to. Yeah, I wanted to go into one more thing here. I think the rational canonical form is also hanging somewhere, but yeah, so this is the phenomena where a minimal polynomial and characteristic polynomial are same. Yeah, right now you should think about that phenomenon. That's a very deep phenomena actually, because if you look at diagonalizable matrices with distinct diagonal entries, they also have this phenomena. Right, right, and it's a very deep thing. Separability, non-repeated of roots. These are some things. And yeah, I will not say it now, but it is a very interesting things. Okay, yeah, all right. So yeah, let's stop here, and yeah, we'll tell you